Okay, so welcome to the 23rd lecture, and we're gonna prove the Nagata-Smirnov Metrization Theorem. And so basically, we're gonna prove that if the space, regularity, and plus the existence of sigma locally finite basis or countably locally finite basis is equivalent to metrizability for a space. Okay, this is the goal for our theorem. And recall that for any index set J, and x, y, and rj, we can define a metric on rj that is defined as such, which is called the uniform metric. Okay? And also recall that in the second version of the proof of the Orson metrization theorem, which you can find in my playlist, so the proof has a couple of steps. The first step is that we show x is T3 regular and is second countable, then it is a normal space. And then we construct a countable collection of continuous function such that it separates points from closed sets. So this is the statement here. So basically, for any x and for any neighborhood, there exists a function from the collection such that it is positive at the point, and other than the neighborhood, it is vanishing. Okay? Yeah, which separates from points from closed sets, which is the name it came from. And third step is we use those collections to define a map that is an embedding of x into a product space. And additionally, if each fn is like shrinking, is decreasing, then we can actually embed x into a metric space with the uniform metric rho bar. And this is our the steps for Orson metrization theorem. And we want to generalize to our case. So to generalize them, our first step is to show that x is regular and it has a sigma locally finite basis is a normal space. And then we construct a collection of continuous functions such that it separates points from closed sets. And then we use those to define a map embedding x in a product space Rj for some j. And then we, for each of them small enough, we can embed x into the metric space, which eventually shows that x is metrizable. Okay, so let's start. And before that, we need a definition, a notion of a G delta set. So the definition is that for x is space, A is a subset of x, that is a G delta set in x if there exists a countable collection of open sets such that A is the intersection of them. Okay? So this is the definition of G delta set. So for some examples, if a set is open, it is automatically a G delta set. And if x is first countable Hausdorff, then for any point, the single point is a G delta set. Well, if we could just pick a U, a countable neighborhood around x, right, by first countability, then we have this is automatically true. To show the reverse, pick y is not equal to x. Then, because it is Hausdorff, we can separate them. Now, after we separate them, because U is a neighborhood of x, right? So there exists a UN such that it is contained in this U. But because U and V are disjoint, which means that UN and V are disjoint because we have this, right? So V is Y is in V, and UN and V are disjoint, so V is not in UN, and X is in UN, right? So, they're not equal, right? So Y is not in UN. If you're not in UN, they're not in the intersection of all UN, right? So y not equal to x, then y is not in UN. By contrapositive, if y is in UN, y is equal to x, right? Another example, if x is a metric space, then closed sets are all G delta sets. The definition, so we just let U C1/n defined as the 1/n neighborhood of C, which is the union of all balls with radius 1/n, like we take a union for all x and c, and then we can check this is true. So C is the intersection of all the UNs from as n runs from 1 to infinity, like all the natural numbers. Well, to show this, first, if X is in C, then no matter what, you are in this ball, right, which is automatically inside this, right, and automatically inside this. Now, if X is in this for all of them, so we want to show this is true. If this is true, then you're in this n equal to 1. So you're this, which means that you are equal to, you're inside a 1 ball centered at x1 for some x1 that is inside C, right? And 1 over 2, so you're in some 1 over 2, or x2 inside C. And yada yada yada, right? 1 over n is xn for some xn that is in C. So eventually, we have a sequence in C such that it converges to X, right, from here. From here, we have a sequence converges to X, which means that you're in a closure, which means that you're in C because C is closed, right? So X is in C. So if X is in this for all, which implies that X is in C. So we're done. With some examples of G-delta sets. To make sure we're not going too far, we need a lemma. We're going to start for some lemmas, right? Okay, so the lemma states that if X is a regular space and B is a sigma locally finite basis, then X is normal. And the closed sets are all G-delta sets. So this is an important lemma. So step 1, we're going to show that for any W that is open at X, there exists a countable collection of open sets such that W can retain as the union of all the UN and even the UN bars. Okay, the equality holds. And to prove this, well, okay, so first we rewrite the basis, and each Bn is locally finite. And we let Cn denote all the B such that B bar is in W. For each Cn, all the B and Bn such that B bar is in W. So this is a subset of Bn, right? And thus C, all the union of Cn, is a subset of B, which is also sigma locally finite, right? Because B is locally finite. C is also locally finite. Now, for each Cn, let Un denote a set like this equal to this. It is open. Okay. Then by the lemma from last lecture, we have this is true. Okay. It's a lecture of local finiteness. I think it's somewhere here. Yeah. Something here given locally finite collection. Okay. This is our lemma. Thus, U bar n is contained in W. Right? Because we have U bar n is equal to all of the B bar, but B is in Cn, right? If B is in Cn, then we have B bar is in W. So U bar n is automatically a subset of W. Thus, we have all the UNs, right, and all the UN bars are also inside W. Now we want to show the reverse inclusion. For X and W, because it's T3, so there exists a basis such that this is true, right? Because by the regularity of X. Now, because B is also in Bn for some n, right? Then B is in Cn, right? B is in B, which implies B must be in some Bn. And from here implies that B is in Cn, right? B is in Cn, X is in B, and so X is in Un, right? Un is this, right? Un is this. X is in B, or B is in Cn, right? So X is in Un. X is in Un, so W U, X in W, X in some UN, which means that W is a subset of union of UNs. Okay, so we have proved the first step. We can express any open set as a countable union of the open sets and the closures of the open sets. Okay. Now with step 2, we show that if C is closed, then C is a G tilde set. This is just by De Morgan's law. Okay. Now we show that X is normal. So for two closed sets, we want to separate them. First, we let X minus D, like we do this by step 1. Okay, so from here, this is equal to this, so UN covers C, right? All the UNs, it covers C. I mean, C is a subset of the union of UNs, right? Because we have this. And all the U bar n are disjoint with D. Okay, from here, we see that all the U bar n are disjoint with D. Again, by symmetry, right? We replace D by C, U by V, right? C, blah, 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 yada, yada, right? Then we construct a new collection. U prime n is equal to this, and V prime n is equal to this. And in fact, we have this is a separation of C and D, okay? Each U bar n is open, right? And they're also disjoint. And this proof is really similar to the lectures from the normal spaces lectures. Okay, so it's in lecture what is the number of the lecture? I think is lecture 16, normal spaces. Normal spaces. I think it's like we do the same construction, right? We're doing the same construction here, right? And they're open and they're also disjoint. And the proof is here. Okay, just by this. Okay, so now we're back to our task. So we're done. Okay, we're done the lemma. Okay. Now, another lemma. If X is normal and all the closed sets are G tilde set, then there exists a continuous function such that it vanishes on A and is positive outside of A. Okay, it's vanishing on A and is positive outside of A. To do this, because because it's a G tilde set, right? So from here we see that A must be in the subset of UN for all n. Then, because X is normal, so we can apply Orzon lemma. Let Fn be a continuous function such that it's vanishing on A and is equal to 1 on outside of UN. Okay? I mean, A and this are two disjoint closed sets. Okay, we can separate disjoint closed sets. And we define, okay, so we have Fn defined, right? Now we define F as the sum of Fn and each is like divided by 2 over n. And as you can see that it converges uniformly by the comparison test or M test, whatever you said, which shows that F is continuous, right? Because each partial sum is continuous. And Fa is equal to 0, right? F is vanishing on A. And also we have, okay, so we have X minus A, which is X minus this thing. By De Morgan's law, it is equal to this thing. And if it's this thing, then if X is in here, then X is in some X minus UN, right? Which means that F of X, we have each of them are equal to 1, right? I mean, at least this is equal to 1, right? So no matter what, it must be positive. At least this is equal to 1, right? So this must be positive. Okay. Alright, so with the 2 lemma equipped, we're gonna finally prove the Nagata-Smirnov Metrization Theorem. And let's just show this first, shall we? So first, if you're T3 and have a sigma locally finite basis by lemma, it is T4 and the closed sets are G tilde sets. And if it's T4 and the closed sets are G tilde sets, right? We have this, right? The closed sets are G tilde, so we have this, okay? So we're gonna embed x into this for some j. So first, just some initial settings. And for each n and b and bn, we can pick a continuous function such that it is vanishing outside of this and is positive on b. Okay? And because this is a closed set. This is a closed set, right? X minus b is a closed set. This is our lemma, our lemma set, right? For closed sets are G data set, and we have a function such that f of this is, and outside of this is positive, right? So this is a closed set, and outside of the closed set it is positive. And then we can just pick a continuous function, right? For each n and each b, right? NB. Okay. Then what we have now is that for any x naught and any neighborhood of x naught, first we can pick some b and bn such that we have this, right? Because it's generated by a basis. Then okay, this should be x naught. I'm sorry. Then we have this is positive, right? Because we're from here, right? This is positive, and outside of u, outside of b, so even just from here, right? From here, we have this is true. So, yep, this is our initial setting. Now, let J be the all such pair such that n is positive and b is in Bn. Okay, so let J be all such pair. Okay, this is a subset of this. This is index set. We're gonna define f, the embedding function, that sends x to this. Okay, to this. And we take this, the product topology, we have f is an embedding, okay, by the previous results. And now since the metric topology on R omega is found in the product, sorry, it's not omega, sorry, shit, damn, my bad, should be RJ, product topology RJ, but I copied directly from my horizontal metrization notes. Should all be okay, because the metric topology is finer than the product topology. So does the subspace, right? Well, U is open in X, then FU is open in FX with the product topology, and is also open at this with respect to the metric topology. Okay, so those are all taken as a subspace of them. So what we remaining to show is that f is continuous. Right? F is continuous. I mean, all the previous result here comes from our horizontal lemma. Sorry, not horizontal lemma. Horizontal metrization theorems. Okay. What we have is injective, same as above. Right, this is my proof of horizontal lemma. Sorry, metrization. So everything is just like similar, and lastly we're gonna show that f is continuous, right? Last thing we're gonna show is f is continuous, and we're gonna show it differently because we don't have countable basis, right? And after we show this, we're gonna spend an entire, okay, so we're gonna spend a page to prove that f is continuous. Well, since we have this true, okay, so we pick x naught and x and epsilon. We want to find a neighborhood such that this is true. This is just equivalent to the continuity of f, right? F big F. So from here we're going to boil down to each component. For each n, we can pick a un neighborhood of xn such that only finally, right, is locally finite, right? So for those locally finite, for those that intersects with un, we let Bn prime denote those collection, okay? And because we have this setting, right, we have this setting from the beginning, which means that only B and Bn prime has this is not empty, right? Because otherwise you are disjoint. If you're disjoint, then remember we have this, right? So only B and those has this is true. And for those B, right, we're gonna by continuity, we're gonna pick a neighborhood of x naught such that first of all we can make it small enough such that it is contained in UN. Okay. I mean this UN is the neighborhood of x naught. We pick a neighborhood that is smaller than UN. This is always possible, such that by the continuity for each, this is a finite collection, right? So this is definitely doable. For each of them, and x is in Vn, we have x and x naught are epsilon over 2 closed. Because, okay, each x and b are continuous function, right? So we can do this. This is doable, and plus this. Okay, so these two conditions, this Vn is picked, and we're gonna, well, this Vn is picked for every n, right? We just run through all the n's such Vn, okay? And then eventually we're gonna pick by our convenient property of 1 over n that is less than epsilon over 2. We just let W equals to this, which is the finite intersection of open sets, which is open. So this W is our desired neighborhood, right? First of all, for x and W, if n or not is less than n equal to n, and for any b and bn, we have this is true. Okay. And the verification is here. And if n naught is greater than n, then because it is a mapping from 0 to 1 over n naught, which means that for any b, no matter for what, any b for bn naught, any two things must be inside this, right? So must be less than equal to 1 over n naught, which is this, because we have this, which is less than epsilon over 2. Thus, no matter what n we chose, no matter what b and we chose, and no matter what x and w we chose, we have this is true. So by the definition, like the supremum, right? This is an upper bound, which means that the supremum, well, the supremum is this, right? Yes, exactly what we needed, right? Fx and w. Oof, so this is what our battle for proving metrizability. Although don't forget that we want to show this is also true, right? So last but not least, metrizable, first of all, is automatically regular, right? Because metrizable spaces are normal. Normal spaces are regular. Now we show that X has a sigma locally finite basis. This is what we want to show. First of all, let's AM, for each M, we let AM denote all such ball is open cover of X. Now again, by the lemma from last lecture. By the lemma from last lecture, remember we show that if any metrizable space and any open cover X, there exists another open cover X that is refining A and is sigma locally finite. So there exists open cover BM refining AM that is sigma locally finite. Okay. Okay. Note that for any B and BM, their diameter must be less than equal to 2 over M. Right? Because this is a refinement of AM. Okay? This is refinement of AM. And okay, so if you forget what is refinement, this is the definition of refinement, okay? So do it yourself. Now, let B denote the union, the countable union of all BMs, where each BM is a sigma locally finite. Each BM sigma locally finite, so countable union of countable sets is again countable. So this is again a sigma locally finite set. Now we just want to show that there's a basis for X. Well, for any such ball, right, we can pick this then as Bm covers X, we have X in some B for some B and Bm. But the diameter must be less than or equal to 2m. And this is less than epsilon, right? And also X is in B. So by the definition of diameter, we have this ball is contained in B. Right? Now, if B, again, like B is B and X is in B, because B is open, so we can pick a basis such as this. So out here, we just verified that the topology generated by basis B is the same as the topology generated by the metric on X. So we have shown that the equivalence of metrizability and T3 plus sigma locally finite basis. Okay, this is everything for this lecture, and I'll see you guys next time. Bye bye.